objects where not all points on the object have the same velocity, where not all points on the object have the same acceleration. Up to this point in the semester, we've been looking at objects that did have all points on the object have the same velocity, same acceleration. So if I were to tell you I've thrown my pencil up in the air, how much time until it comes back down and lands? When you wrote down F equals ma, you didn't have to worry which point or which acceleration is it. What we assumed was that the entire marker had the same acceleration and velocity. So if I asked you for the velocity of the marker, you didn't all put up your hands and say, the velocity of the cap or the velocity of the end. Okay? That's now changing. So we're considering objects that in addition to moving, might be spinning. If an object is moving and spinning, then the velocities of the different points on the object are not all the same. The classic example was the case of the wheel. We studied the wheel for the second half of the class last week. Different points on the wheel all have different velocities. Different points on the wheel all have different accelerations. So we have to find a way to manage this other than just saying, okay, let's divide the wheel up into a million different pieces and write F equals ma for every point on the wheel, and you've got a million equations and a million unknowns. That's miserable. We don't want to do that. We want to develop a little bit of theory that we can then use that will allow us to treat this object with a much smaller set of equations. We developed one relationship which was almost so obvious you felt like we maybe didn't need development. But the relationship we developed last class was that if I start with F equals ma, that was what I could use if it was all moving the same. I would write that as the sum of the individual forces acting on the individual masses with their individual accelerations. After a little bit of work, we showed that we had the sum of the external forces equals the total mass times a bar. What did a bar represent?
The center of acceleration.
Well,
Center.
almost. I mean, a bar, Zach said the center of mass. A bar by itself is not the center of mass. The center of mass we would call
The acceleration.
X bar. Yes. A bar is the acceleration of the center of mass. It is not the acceleration of any random point on the object. It is the acceleration only of the center of mass of the object. Suppose I have a wheel rolling along, and it's rolling along, maybe it's attached to a car, and the car has a steady velocity of 10 meters per second. Suppose I'm considering only this wheel. What is a bar for that wheel? 0. I agree. The center of mass of the wheel is just moving exactly along with the car. So the center of mass of the wheel has no acceleration. What is v bar for the wheel? 10, correct. What is x bar for the wheel? Now that question, your answer should be, and I'm not trying to give you a trick question, your answer to that should be, it depends. X bar compared to what? Where's the center of my universe? I think maybe some of you were about to say the center of the wheel. Is that what you had to give some answer failing some other set of coordinates? You just say the center of the wheel. So in the case of the center of the wheel, the acceleration of its center of mass is 0. Is the acceleration of point A in the front, is the acceleration of point A 0? Assuming the car is moving at a steady speed of 10 meters per second. No. In fact, how do we go about calculating that? If I wanted to figure out the acceleration of point A, the acceleration of point A would be equal to the acceleration of the center of the car, or the center of the wheel, which I'll call AG for center of mass, plus the acceleration of point A compared to the center of mass. The acceleration of the center of mass of the wheel would be 0 in this case. The acceleration of point A compared to the center of mass, I can write out in radial and transverse coordinates as r double dot minus r theta dot squared divided by r theta double dot plus 2r dot theta dot. The r double dot will be 0 because the radius, the distance from point A to the center, is not changing. The r dot will be 0 because the same reasoning. The theta double dot in this case would also be 0 because in order for theta double dot to not be 0, the rate at which the tire is rotating would have to be going faster and faster and faster. And if the car is moving at a steady speed, then theta dot is also a constant. So that's also 0. So the acceleration of point A compared to the center of mass would be minus r theta dot squared. If I told you the radius of that tire, you can calculate theta dot and actually get a number. My point right now, though, is just to indicate that the acceleration of point A is not 0. The acceleration of point B is not 0. The acceleration of point C. In fact, the acceleration of none of the points on that tire are 0 except the exact center. This equation, though, you can always use. So if you're looking at some solid object that may be rotating or doing who knows what, the sum of all the external forces acting on it equals its total mass times the acceleration of the center of mass. Okay, so we can use that. The next equation I wanted to develop, we got kind of partway done this last class, was I want to have some similar relationship for sum of the moments equals h dot. You'll get nowhere in statics without both of those equations. Of course, in statics, sum of the forces equals 0, sum of the moments equals 0. But you can't do statics with only half of it. So, same thing with dynamics. We can't do dynamics with only half of this. We need both of these pieces in order to be able to analyze problems in dynamics, how objects are moving. So we have to fill in the second half. And that's what we started to do last class. It maybe felt like a little tedious, but we have to go through this so we know where this comes from. So, just to restart and go quickly through what we went through last class, sum of the moments equals h dot. H dot was r cross ma. Now h was r cross mv, it's angular momentum. And when I take a derivative of that with respect to time, I get r cross ma. So this is a h dot, and what I'm going to do is write h dot, or this equation, sum of the moments equals h dot. I'll write that for every little particle on the wheel, every little particle on the moving object. So I'll write that out for every particle. I'll get a million equations and a million unknowns. And then the catch here is I'm going to add them all together. So this summation sign says I'm adding together all those equations. I'm writing this out for every point on the object, and I'm adding them all together. After I've added them all together, my moments equals r cross f. You may not be surprised, like we did last class, to take that f and write every force as a combination of an external force plus internal forces. The forces internal to an object will all cancel out. So for example, if James is one of the particles inside the object, there's a force acting on James due to Vaughn. There's also a force acting on James due to Aaron. But if I'm adding up all these total forces, if I add up the force of James on Vaughn and the Vaughn on James, those two forces are equal and opposite. They're both sides of the same force, so they're going to cancel out. So when I add up all the moments due to all the forces on all the particles, it's only the forces that are acting on the object from outside the object that are going to matter. So this will end up being the sum of the r cross external forces, because all the internal forces acting on the objects are not going to matter. Okay, so this is a sum over I from 1 to n, where n is the number of chunks or particles we're dealing with. Let's focus on the right-hand side. I've taken the acceleration of any individual particle and written that as the acceleration at the center of mass plus the acceleration of that individual particle compared to the center of mass. The acceleration of the center of mass, we might write as a, this is the acceleration of the center of mass, I might write that as a sub g. Another common term for that would be a bar okay, to indicate it's the acceleration of the center of mass. And one thing we did last class was we wrote this Ri cross ma bar plus, and I wrote the acceleration of point I compared to the center of mass as a vector, but I wrote that vector in radial and transverse components. So that was r double dot minus r theta dot squared 2r dot theta dot plus r theta double dot. This is in the radial and transverse components. We made an observation that this r and that r are the same.